Hey everyone, this is the first of several video clips that I'm going to put together for you guys that's going to outline the coursework picking up from section 4.2. We finished through 4.1 in class, so this snippet is going to be on section 4.2. I'm going to try to create clips that cover each section and just do one clip per section so that you guys can sort of watch them at your own pace. And then I'm going to create consolidated clips that go over several sections together full of homework problems. I might send you one or two of these clips just to get your feedback before I put together a bunch of other ones, and you guys let me know what you think. So let's get started. 4.2 deals with the natural exponential function. So we, a couple of weeks back, already started discussing exponential functions. In general, what those exponential functions were, how they varied from functions that you were used to seeing. We were used to seeing beforehand a function like y equals x to the third plus fourth, something of that nature, where we have a variable in our base. Now we're going to have our variable in our exponent, right? And that's what's going to give us an exponential function. So an exponential function is something like y equals 3 to the x plus 4, as opposed to x to the third plus 4. So our exponent is in the power. We saw in 4.1 that this allows our function to grow at a much faster rate. They're also much more interesting to deal with, and they have many real-world applications. We discussed compound interest last week. We'll see in 4.2 that there's actually another application dealing with a specific or special type of exponential function. So 4.2 deals with the natural exponential function. We see on slide 72, which is the first slide on 4.2, that we're discussing an exponential function with a base of e. Now, a lot of people get confused about e. All e is, it's a letter, alright? All we're talking about when we say e is we're using e to represent a number 2.718, roughly, approximately 2.718, like pi. Pi is approximately 3.14. E is approximately 2.718. That's what we're using E for. It's a special number. It wasn't just pulled out of a hat. This isn't, again, it wasn't really an honors math class, so I'm not going to go into the whole, where did this breakout of E come from. It's in your textbook. It shows you how they got to E. It takes a little bit of finesse. Better understanding of calculus would actually help you get there. But we actually see on the same slide, the informal definition is E is a number that 1 plus 1 over n the number that 1 plus 1 over n to the nth power approaches as n gets bigger. You're not responsible for the definition. You're not responsible for the derivation. We are going to be using applications of E though. So what do you have to know about E? Firstly, understand that it's just a number. It's like saying 2.718. So when we get to the next slide, 73, which has the exponential function y equals e to the x, understand that y equals e to the x just means 2.718 whateverness to the x power. It's like saying 3 to the x or 5 to the x. E is just representative of another value, so don't freak out when you see it. Here we have evaluate e to the 5th, evaluate 3 e to the 5.5. That's something that you can easily do in your graphing calculators. So you can take your graphing calculator and type in y equals e to the 5th power. Right? Let me grab my graphing calculator 1 second. So where can you see E on the graphing calculator? Right above the on button, right here, you see the LN button. It's the third button from the bottom left corner. Right above that you'll see e to the x. So if I hit second e, it says e to what power? So I can type in a 5 and it'll evaluate e to the 5th power as being 148 roughly. So that's all it tells you, right? E is again just a number and I'm raising e to the 5th power. We're going to see why it's so special. There's a particular application where we're going to be using e. If I want to graph functions with e, graph y equals 3e to the x plus 2, for instance. That's the next ask on the same slide. Well, we saw last week that when I had the graph of a function of y equals a to the x, where a was between, where a was greater than 1, we saw that the general graph or shape of that graph looked sort of like this, where the graph went through the point 0, 1, right? And it had a general shape where as we approached positive infinity for the x's, the y's approached positive infinity for the y's. Now, since e is bigger than 1, it's roughly 2.718, the graph of y equals 3 e to the x plus 2 should have a similar shape. Since we're multiplying e to the x by 3, it's like saying we're vertically stretching the graph because we're multiplying the outputs by 3. We are also doing a vertical shift plus 2. So you can sketch the graph by taking the basic function, my timer. So by taking the basic function, shifting it up, and also vertically expanding it. You could also graph this in your graphing calculators. You go into y equals, and you can type in 3 second e to the power x. Back out and then hit a plus 2. So that's what my calculator screen reads. 3e to the x plus 2. And now that I graph it, you can see as the calculator is being graphed out, what the function will look like from a standard window. X is negative 10 to positive 10, y is negative 10 to positive 10. So that's what we're looking at here. When we have a standard function, right, that is being stretched out and then we're adding 2. Now, I don't know, you're not really going to be asked to graph exponential functions, so I wouldn't worry about that too much, within pre-calculus at least. What's going to be more important is your ability to understand the power that exponential functions have over standard polynomial functions and their special or different uses. And we'll see that more on the next slide. So I want you guys to go over to slide 74. Here, we know that we have a specific value of e. We know how we sort of got there, right? Cheated. Now, we're going to give you one application of how to use e. Last time we met, we discussed how to find compound interest, or how to calculate, let's say, money in a specific type of account if interest is broken out in specific cycles. So if I had 12% a year and I broke it out to 5%, 12% a year and I broke it out monthly, or 12% a year and I broke it out quarterly, or daily, what the implications would be. we had a special formula. A of t is p 1 plus r over n to the power of n times t, where p represents principal, r represents the rate, the annual rate as a decimal, n represents the number of compounding cycles, and t the time in years or months or whatever the cycle is. So if I had 12% a year, then this would be a 0.12, that would be however many years. Now n would be the number of compounding cycles. So we discussed if this was 12 times a year, n would be 12. If it was 4 times a year, n would be 4. So it would be 4 times a year times the number of years would be how many times we'd raise it, this value to that power, right? Because we're getting paid interest on our interest more frequently. Now, how does this change when we're not compounding interest monthly, quarterly, weekly, or daily? If we think about time is not necessarily going to be broken out into intervals that can be exactly measured. If you think about, let's say, the Olympics, an Olympic swimmer will swim at a specific time, their laps that they're doing, they're not going to be swimming in exactly 24.7 seconds. You'll see that the time gets cut up actually to even milliseconds. But that doesn't mean that I could break time into milliseconds. And that's because time is what is known as a continuous variable. It's continuously moving. It's hard to break, it's impossible to say, okay, I'm stopping you exactly at 10 o'clock. You're going to stop somebody at 10 o'clock and a specific number of seconds or milliseconds. Within this realm or sphere, we've also developed the type of thinking where you can compound interest not just monthly or daily or weekly or quarterly. You could actually compound interest what is known as continuously, which is every millisecond of a millisecond. You can calculate interest on interest on interest all the time. This would obviously get you a max payout when you're looking at all the different versions or scenarios. It also gives you a different formula. The formula you'd have to use for compound interest, which again is on your slide, if they say interest is compounded continuously, you have to use a different formula. A of t is equal to p times e to the power of rt, where p again is your principal, e is the number 2.718 whatever, which you can get directly from your calculator without having to round. R is the rate at which you're compounding, and t is the number of cycles. Notice, the n's are no longer there because we're not compounding 12 times a year or 4 times a year or 1 time a year, right? We're compounding continuously. So if you're ever told, calculate, if I were to invest $7 million at 5% annually, compounded continuously, not compounded annually, not compounded monthly or weekly, this is the formula we use. Again, all in the slide, everything is labeled out. P principal, R rate as a decimal, E is the irrational number 2.718, but your calculator has E, and T is the number of years. I'm going to work out the problem that's on the slide for you as well. Find the amount in John's account after 8 years if $1,000 are invested at 12% per year compounded continuously. So if I put in $1,000 into John's account, that's the principal. That's how much money goes into the account. It's invested at 12% a year compounded continuously. I'm not going to use my standard compound interest formula, p times 1 plus r over n, close parentheses to the power nt, like we did in 4.1. Because we're compounding continuously, we're using a new formula. I'm going to multiply 1,000 by e to the power of the rate. The rate is 12%. So I'm going to use 0.12 times time. The number of time, what did we say? 8 years. So in order to minimize error, I recommend evaluating the exponent first. 0.12 times 8. That gives me 0.96. Then I can go into my calculator. So I did 0.12 times 8, get 0.96. Then I'm going to do second e to the power of the answer. E to the power answer. How do we get answer? Well, you see it right there. Where'd it go? Right above the negative symbol, answer. So if you do second answer, you can actually never retype the line right above the 0.96. I don't have to retype it. I could just do e to the power answer, and it's going to type in the answer from the prior line. So e to the power of 0.96 is 2.611. I'm going to multiply that by 1,000, and I'll get, after 8 years of compounding continuously, my $1,000 became 2611 and 69 cents, or 70 cents if we round to the nearest cent. Now, if you guys want to test this out, you can see, does it make sense to go into an account that compounds continuously, or does compounding monthly or quarterly pay out better? Well, I challenge you. Take this problem with John. If he had $1,000 and he put it in an account that compounded monthly, or weekly pays out more than monthly, daily pays out more than weekly, so do daily. You do 1,000 times 1 plus 0.12 over 365 to the power of 365 times 8 years, it's going to be less than this. So we did the problem last time where we showed that quarterly was less than monthly, and monthly was less than weekly or daily. Well, you'll see that all of those are less than continuously. Continuously gives you the highest payout. And that's it. This was a very short section. This section was only a 3-slided section. So next topic will be 4.3, and we'll cover that shortly. Alright? Make sure to email me with questions, and I'll be compiling, again, 4.2 homework questions together with a bunch of other questions, and we'll put it together as a separate video, different types of problems worked out.